Maybe centrifugal force will dislodge it.
No, then, most certainly.
If we'd been paying more attention to our work, this might not have happened. Doug?
Okay, today we're talking inverse and composite functions. The goals: to identify a one-to-one function using what's called the horizontal line test. That's goal number one. Goal number two: to find the inverse of a given function, whatever that is. Goal number three: to compose functions. I've got some definitions for you. Definition one: a function is one-to-one if none of its ordered pairs have the same second coordinate. Okay, back up. What's a function? A function, remember, is a set of ordered pairs in which no two different ordered pairs have the same first coordinate. Does that sound familiar? So it's got to pass the not the horizontal line test, but the vertical line test for it to be a function. So what kind of functions have we looked at in this class so far? Well, the quadratic comes to mind because we just got done talking about it, right? A quadratic function will open up or down, one or the other, and it has the equation f of x equals ax squared plus bx plus c. It's a degree 2 polynomial equation with two variables, right? F of x could be considered y, so x and y are the variables. But we've also looked at linear equations, right? Linear functions. So f of x equals mx plus b. We've looked at others. We didn't necessarily name them, but we've graphed plenty of different kinds of equations. I'll just give you one more example. How about f of x equals absolute value of x? We've graphed that. Probably the first week of class we graphed that. Anybody remember what the shape of that graph looks like? Anybody remember the shape of f of x equals absolute value of x? Oh, I see the V shape, yeah. So that's a V shape, and then if you stick a negative in front of it, it actually becomes an upside down V, right? So which of these graphs do you think will be one-to-one? Yeah, the first one for sure. Let's read the definition again. A function is one-to-one if none of its ordered pairs have the same second coordinate. So second coordinate controls what? The horizontal stance or the height? No, second coordinate controls the vertical. First coordinate controls the horizontal, right? So we're talking about the second coordinate. No two different ordered pairs should have the same second coordinate if it's going to be a function. So certainly in a line, at least this line that I've drawn, all the heights of all the ordered pairs that make it up are different, right? So this would be a one-to-one function. But any horizontal line will get me to a height that's 2 points on this. Well, not a horizontal line down here, but any horizontal line that goes through the graph of a parabola will get me to 2 points on that graph that have the same second coordinate, right? By definition, if these 2 points go through a horizontal line, they're at the same height, they have the same second coordinate. Likewise for a V-shaped graph, or upside down V or upside down parabola. So these last two are not one-to-one. So a one-to-one function isn't going to have any peaks or valleys in it, is it? So a one-to-one function doesn't have to be a straight line. Don't get the wrong idea. But it does have to either go all uphill from left to right, so there's a one-to-one function, or all downhill from left to right. You can't have any peaks or valleys. So these guys are both 1, 2, 1, 1, 2, 1. Okay? So let's talk about definition number 2. The inverse of a function f is the set of all ordered pairs obtained by reversing the coordinates of each ordered pair that comprises f. So every y becomes the corresponding x, every x becomes the corresponding y. So let me give you an example then. How about f? Let's use, we can just use a finite set of ordered pairs to define a function, right? In fact, if you think back, way back to the beginning of the semester, I probably gave you something that looked like this as a function. 1, 2, 3, 4, 5, 6, and how about 7, 2? Would this be a function, by the way? Yeah, no two different ordered pairs scan it. No two different ordered pairs have the same first coordinate, right? Now, you said no because you're thinking one-to-one. It's not a one-to-one function because I see two different ordered pairs that have the same second coordinate. So a good note to make is it's not 1, 2, 1, right? But it is a function. So what's the inverse of the function? How could you create the inverse? Well, if you follow just the definition, just reverse all the ordered pairs. So what would you get? I'll do the first one, 2, 1, instead of 1, 2. What would be the next one? 4, 3, the next one? 6, 5. And the next one? 2, 7. Is it really that easy? Yes. I feel like I'm selling you inverse functions. It's really that easy for only $19.99, plus shipping and handling. Okay, so you just reverse all the ordered pairs. So it's really easy if you just have a finite list of ordered pairs. You just switch x and y. Now, what's the problem here, or you may not realize why it's a problem, but what's different about the inverse, which, by the way, we would call the inverse f and then superscript -1. Now, that's not an exponent. Okay, we call that when you see the f superscript -1, we just say f inverse. F inverse. There's a reason for the notation, which I'll talk about a little later, but don't think of that as an exponent. Think of it as a superscript. F inverse. When you see f to the -1, f inverse is what you say. So we almost observed this already. What is f inverse not? It's not a function. Because since we switched something that wasn't one-to-one around to create the inverse, we got an inverse that's not a function. And that actually is a huge problem because all the theory in calculus, at least introductory calculus, is based on functions. And why are functions important? Here's a good example as to why a function is important. Your calculator is kind of like a function machine. Think about it. The inputs, like if you're adding the inputs, you input two things, right? 1 plus 2. So those are the inputs. And the output, well, in order for it to be a function, you better get one output. 1 plus 2 is 3, right? You don't want two different outputs for 1 plus 2. That would be a huge problem. So that gives you an idea of why it's a huge problem here. At least you run into that same kind of wishy-washiness if you don't have a single output in the applications for functions. So we want the inverse to be a function as well as the original guy we started with. So how do we accomplish that? If you think about it, note number 1 tells us what has to be true. Every one-to-one function has an inverse that is also a function. If the function's one-to-one in the first place, if you flip all the ordered pairs around, it'll still be a function, won't it? Because you won't have any first coordinate going to in the inverse. You won't have a first coordinate applied to two different outputs, will you? So in other words, if you ensure that f is 1-to-1 in the first place, you're not going to get something like this, where you have the same output for two different inputs. And if that doesn't happen, then when you switch them around, you won't have the same input for two different outputs, so that the inverse will be a function. Okay, so that was note number one. Note number two, the domain and range of a 1-to-1 function and its inverse function are flip-flopped. That's a very technical mathematical term, right? Flip-flopped. So, okay, think about this in terms of the domain and range of well, this isn't really, this guy's not a function, but we can still think of the domain as the set of all inputs and the range as the set of all outputs. So what's the domain of f? The domain of f is, just look at all the inputs, 1, 3, 5, and 7. Remember, domain is the set of all inputs. What's the range of f? 2, 4, 6. No repeaters, right? So that's the domain and range of f. You could still have a domain and range of f inverse even though it's not a function. What would the domain then of f inverse be? 2. The inputs are 2, 4, and 6. Oh, just like the range of f, right? And what's the range of f inverse? 1, 3, 5, and 7, just like the domain of f. The domain and range are flip-flopped. Whether it's a 1-to-1 function and the inverse is a function itself or not, the domain and range are flip-flopped.